let's get started with what we as analog devices can provide in regard of motor and motion control. So you can see, starting from the bottom here, that we can provide solutions up the stack, essentially. And we are a semiconductor company, right? So what we do provide is integrated circuits, chips, to essentially drive motors. So we have everything available. If you have an application that has any movement, needs motors respectively, to design your own electronic with our integrated circuits. I skipped the motion cookies for now and go to the modules here. So the modules are essentially turnkey solutions. So over the time, our customers said, you have great technology, excellent features in your integrated circuits, but we don't have the resources, we don't have the time to essentially develop our own electronic. And this is when we started our modules. These are off-the-shelf solutions to essentially drive motors, right? From a single axis up to multi-axis, 6-axis on one board, or with a high-level interface up to, I don't know, how many you need in your application, essentially. So we also offer so-called motion cookies. We have an extra slide for that, so you get an idea where this name is coming from. But these are essentially little electronics. If you think about a Wi-Fi module that you can solder on your own electronic, this is the same idea and concept. So you would take these little motion cookies, design the footprint on your electronic, so you can actually solder it on your electronic to enable motor control very easily without much software and firmware work. Additionally, we have our so-called pen drives. So these, you can see, are actually mechatronic solutions. So it's the motors with the electronic attached on the back. And here we see two examples. On the left, we see one with an I/O link interface, and on the right one with an EtherCAT interface. There is more, like RS-485 and so on, we talk about later on. And then we have our software and tools. So essentially, we have one graphical user interface called TMCL IDE that can be free downloaded on analog.com to support all our electronics, right? So you can connect our evaluation boards, our off-the-shelf solutions, our pen drives to easily explore and use our solutions. Going to the next slide, we see one of our pen drives here, right, in the middle. And there is some color coding. So the pen drive here is completely in yellow, so to say, which is our ready-to-go solutions, right? If you need a fast motor and motion control solution, take a pen drive, integrate it into your system, and it's very easy to essentially operate the motor. Then we can see like this circle here with purple and orange, which represent essentially our integrated circuits, right? Obviously, our solutions use our ICs, so having everything on the feature side and technology in our ICs, so we use it for our electronic and pen drives, and then our software, which is our graphical user interface, right? So essentially an easy access to motor and motion control, reliable and sustainable. Yeah, here we have an overview of the motors that we support. We see it on the left side here, our stepper motors, right? So these motors are typically selected if you need high torque with a low to medium velocity range. These are very great fit for this, for accurate positioning and velocity operation. Then we also support to drive brushless DC motors, EC motors, which are typically used in applications when you need high dynamics, high speed, but you probably need some sort of closed loop, so an encoder. The good thing is they have a long lifetime and very efficient, so it's essentially the highest efficient motor type when driving them field-oriented control that you can get. Then we also have solutions on our portfolio to support brushed DC motors. They typically have low requirements on positioning, speed, and precision, and typically a shorter lifetime, but deliver high power, essentially, on a small space. And then what we also support is driving essentially solenoids like valves We have pretty neat features, products for that, and these are simple on-off actuators essentially, or for example proportional valves to position and to get essentially to switch things on and off, if you will. Yeah, here we see some ideas of applications. So this is the typical applications where you would find these motor types. So for steppers, just to name two, CCTV and conveyors. But as you have the material, you can check it later on as well. Brushless DCs with robot joints, AGVs, or e-bikes, for example. Brush DC, more like for white goods and toys, things like that. And the solenoids would be something for relays, contactors, and proportional valves, electronic brakes, essentially. And here a quick overview, just to give you an idea what products we have available. So these are integrated circuits, from the left, from steppers, to the right, to solenoids. So these are essentially the latest generation of integrated circuits that we can offer. So just to give you an idea which products you might want to look into for the different motor types. Here is a summary for the different motor types. So you see essentially the stepper motors, the brushless DC motors, and the DC motors when talking about rotational motors, right? You see the graph, the torque velocity graph, and you see if you have a, let's say, lower velocity range but need a lot of torque, you can use a stepper motor. So without a gearbox, a stepper motor can give you a lot of torque output, right? If you need high speeds, high dynamics, but maybe not that much torque, a brushless DC motor might be a good fit. If you need both, essentially, you would take a brushless DC motor with a gearbox, and the DC motors are somewhere in the middle, right? So, and you can see the summary of the, let's say, benefits and maybe things to consider selecting these motor choices, right? So stepper motors, highest accuracy for an open loop system without feedback, relatively low priced. Brushless DC motors need feedback, right? So you need an encoder to get the precision that adds system cost, but that's why it says costly. And for the DC motors, offers a limited lifetime as you have the brushes inside, right? So there might be more maintenance needed in the application. It's cost effective though, and delivers a high power density. So that's maybe a great starting point in your application if you are looking into your requirements, right? All right, so here we have a look into the stepper motors pros and cons, essentially. So as Planck's stepper motors are well known to be used if high torque is required from standstill, right? From from low speeds to let's say medium velocities. We have a lot of technology to make steppers smarter, more efficient, right? Get more diagnostics out of the system, to essentially enable the best, essentially what you can get with stepper motors. And here's essentially a summary what we can do. So the stepper motors provide precise positioning without any feedback in open loop, right? So without any encoder. There's no gearing required typically, which is a big benefit. That's why it's so cost effective. And the driver circuitry is comparatively low in cost. And what we see here on the right is some challenges you might face in red with stepper motors. So they are known to be not the most energy efficient one compared with the brushless DC motor, for example. And here we have a technology called CoolStep, which we will have a look into later. They are tending to be quite loud, right? So they generate audible noise. And here we have a patented current control mode and high microstepping with stealth chop spread cycle and 256 microsteps, which we will look into as well. Overload conditions may be undetected as we don't have any position feedback. Here we have our stall guard feature, and the motion might be jerky. So here we have a so-called hardware motion controller implemented into our ICs to bring you essentially a good experience in regard of driving the motors with limited jerk. Here we have the brushless DC pros and cons. As mentioned on the left side, we have like a motor that can drive fast and high dynamics for low resonances, high power density, high accuracy if you use a proper encoder. And this closed loop control gives you essentially the most enhanced efficiency compared to other motor types. On the other side, the challenge might be that they are expensive, right? In that case, you can always consider using a stepper motor or a brush DC motor. It requires position feedback for accuracy. So in that case, we also can offer with the steppers open loop with stall guard, like a good solution in comparison. Offers low torque from standstill, so there you need to use a gearbox, right? Or also a stepper motor might be an option, and the cogging torque at low speeds. So here we have a solution in one of our integrated circuits, which is a pure field-oriented controller in hardware, right? So actually that would also address these kind of challenges, having this field-oriented control in hardware. Yeah, here we have an overview of the let's call it pain points and their solutions. So what can we provide to help in certain challenges that you might face in your application? So it's if you face like audible noise, mechanical resonances in your system, with stepper motors, we have a technology called stealth job. So this is essentially eliminating the audible noise from your stepper motor and enables even smoother motor run, right? The other thing, if you use a stepper motor, open loop, you might have the challenge that there might be dynamic load changes, or there might be potential position loss by an overload condition. So here we have a feature called stall guard that enables sensorless back EMF detection. So with the back EMF, you can essentially get feedback how much load is on the motor shaft. When using a brushless DC motor, you need efficient and highest dynamic servo control. And here we have our dedicated hardware field-oriented control IC controller that can actually also be used with brushless DC motors, with stepper motors as well, and with brush DC motors. This is also possible, but typically it's used by brushless DC motors, right? Energy consumption and heat and power dissipation is always a challenge in applications. Here we have our so-called cool step technology that uses the stall guard feedback to automatically adapt the current with stepper motors. Step loss during standstill is something that you typically cannot detect with an open loop stepper. Here we have our brand new tricoder feature, which essentially allows you to count the steps when manually moving the mechanics without additional feedback. So that's something we also have a look into later, also with the demos. Then jerky motion, position overshoot. So the classic approach might be that you do your motion control all in a microcontroller, and we have this all in a hardware algorithm integrated into our ICs. Okay, so and now we look into stepper technologies and solutions. So here we see a typical stepper architecture. Obviously on the right you see your motor, that there might be a host controller with a field bus, and then an MCU. What we can offer is essentially a one-chip solution to drive your motor. So essentially from MCU with an SPI interface that is typically our main interface, or like a UART protocol interface, you would communicate to the motion controller, and with this one-chip solution you get essentially a complete solution to drive your stepper motor, right? So from the motion calculation, like the ramping, over driving the motor with all our smart features, we can provide you with a one-chip solution, but we are also flexible. If you need high power, then it might be that you need external MOSFETs, and for this we also have a solution. So we have a lot of different combinations to drive your motor in your power class. And to give you an idea, we see on the bottom here what motor sizes we roughly cover. I mean, they can be smaller, they can be larger, but essentially motors that you can still hold in your hand, that's the motors we support. So no big AC induction motors, at least as ADI Trinamic, we have, of course, solutions with an analog for that as well. Motor power from milliwatts to kilowatts, and voltage ranges from single cell 1.8 volts up to 70, 80 volts, essentially. Yeah, now we look a little bit deeper into like microstepping. What does microstepping mean? So essentially, if we look to the left here, we have a stepper motor, right? So this is like our stepper motor, how we can drive them. This is full stepping mode, right? So essentially how the coils are controlled via the current is essentially this pattern. So the red one is one coil, the blue one is the other coil, and if you look at the rotor, stator of the motor, this is the movement you would get. You can see that there is essentially 4 positions with this kind of simplified stepper motor, which is of course not the nicest way to drive a stepper motor, especially with low velocities. And I mean, to get like finer movement already, we have the so-called half stepping, which is nothing really fancy, but this is like the current pattern how it would look like here. So we get essentially double the positions from a stepper motor. With this simplified model, it's 8, right? So you could think of that as a very simple stepper motor. And how would that look like? So we have a little analogy. If you think you are riding your bike, either you would ride it with rectangular wheels, which is probably not the nicest experience. With half stepping, it's getting a little bit rounder, but still probably not the best experience to drive this bike. So what can we do? If we look on the left side here, we have an oscilloscope shot. This is the current of one motor phase and the current of the second motor phase. And we essentially use a feature of the oscilloscope to plot the currents via an XY plane. So this is how it would look like if you drive the stepper motor in full step mode. It's a rectangular shape. We see it here with the bike on the right side. This is how the current would look like. And then we also see the half stepping that we looked into already. But how to get even smoother movement, right? How to make the best out of a stepper motor. We actually, with our solutions, provide 256 microstepping. So that means every full step of the stepper motor gets divided into 256 microsteps. And if you think about the bike, now you get the nice experience with round wheels. That's what you want, of course. And yeah, it's a great way to explain it. Here we see it essentially what happens if you full step. It's essentially like showing you the mechanical response of the electrical signal, and the stepper motor is nothing else than a spring mass system. So you can see that there is oscillation here. When you use the half stepping, it's getting better, but with the micro stepping, that's actually the best experience you can get from a stepper motor. Okay, and here we look into a feature. You might already have an application where you have your software written, essentially providing step direction inputs, step direction signals to your inputs of your driver that you might use right now. So you might think, if I want to use the 256 microsteps, I need to adapt my software. What we have implemented into our drivers, if this is like the step generation to drive your stepper motor, which might look like this with 16 times microstepping, we have a so-called feature microplier that gives you, with just changing one register setting in this driver via SPI, the benefit of our 256 microstepping. So this is your step input signal, and with the microplier you get a 256 smooth motor run essentially activated. Okay, and now we deep a little bit more into the technology. For that, I hand over to Dirk.
Yes, of course, to do this microstepping and all these nice features, we of course need current regulation. And for a current regulation, we need first of all a nice current measurement. So I don't want to go that deep in the detail, but one nice thing we have with our latest chip is an integrated current sense measurement. So we are utilizing the MOSFET and the R-on to have a signal which we can measure to get an idea about the current. If you take a look at this picture here, you will see on the left-hand side there would be the motor. Here's a half bridge, and on the low side we have a current sense amplifier, which gives us the value. Now people are coming and asking, hey, there is a very dynamic behavior of the MOSFETs when they get hot. Do you have a compensation for the temperature? And yes, we have. I will not go into that detail, but there are some proofs at minus 40 degrees, at 25 degrees, and at 125 degrees. We are having a pretty good accuracy over the current. So if you have an external sense resistor with a 1% accuracy, and you have all this other amplification factors, you will end up at the same accuracy with a few percent. So this is a very, very nice feature, so that saves BOM cost and also power dissipation on the board, because this is lossless. We have also the capability to adjust the low side MOSFET by, in the end, switching MOSFET parts in parallel to reduce or increase the RDS on to gain the signal or to not gain the signal. So now we have a nice current signal. We can now go on current control. So we have an inductive load, and we have normally two H bridges to drive one two-phase motor. Here you see on the very right side one H bridge and with a connected inductivity. And to control the current, we have now three cycles we use. We have just an on phase where the current flows in the direction where the switches are closed to get energy in the coil, which we call the on phase of the motor. Because we have high dynamics and we need to also get the energy out of the coil, and we cannot wait until this is done or happened by the motor resistance itself, we have the so-called fast decay phase. In this phase, we just put the voltage against the current flow in the coil, and thus we just get a fast decay phase. We just push the current to down. And then we have a very smooth slow decay phase where we just let circulate the current within the coil and the MOSFETs, and the only thing that brings down the current in the coil is the resistance of the coil and of the FETs, the losses. So these are basically the three phases. If we are talking about the current control, we have the on phase, the fast decay phase, and the slow decay phase. And on the left-hand side, you see the graph Lars already explained with the XY mode on the oscilloscope. And you might have noticed already that with this classic control chopper, the target current is not the average current. So we just increase the current in the coil to a value where we stop the fast decay the on phase, and then go down, but we have then lower average. What does it lead to? It's just a plateau at the zero crossing. So a sine wave with a zero crossing just leads to a plateau, and then we can make the sine wave as smooth as we want. With a plateau, all of the smoothness is gone anyway. So we see then that we have a jerky motion in the motor again. So this is something which can be compensating by putting the average up, but that's not the nice way we want to do it. So this is a feature we do not want. We have something against it. We have the patented spread cycle chopper, where we have one more slow decay phase. We just added a slow decay phase after the on phase with a certain time we can set. And after that, we just see then the fast decay phase, after followed by a second slow decay phase. What we can see here now very good is that we are moving around the target. This is called a hysteresis chopper, because we have a hysteresis around the target, which makes it very nice. Even if the target is zero, we are just going a little bit around the zero and then have a very clean zero crossing here. That is very nice, and you see here when it would be zero, then it would not go down here anymore, it would go up here. So it's also for EMC, it's a good thing. So we try with that chopper. We have an auto-adapted fast decay phase. So the on and the fast decay are just determined and terminated by the driver chip itself to have then as this phase is as low as possible, because the fast decay phase is the phase that is consuming much energy, and so we try to just use the slow decay phase. So we have no jump at the zero crossing, a very symmetric waveform, and we have an exact representation of the current we want to have. And this is a very nice feature which we use to drive a very exact and nice current in this. Yes, and I can tell a lot, but pictures are telling more than words. So we see here a very nice sine wave from our chopper, and we tuned the competitor path to the best. So this is really done, not making the others bad. It's just try to have a fair comparison. And this is what we see here. We have there compared just two parts, and you see one has a very steep increase at the zero crossing. And you see also this is just seems to be a 16 times microstepping, so a microplier would have helped here in this case. And you see competitor 2 doing a little bit better, but in the zero crossing it's still a little bit messy, and there is a jump in this current. And additionally, there is then a very high noise on the current, which we are trying to avoid with our solutions. And this translates very good, and I guess no further explanation needed, to the bicycles. You can have the bicycles with round wheels or these with the bumps. So chopper is not just chopper. I guess we make there a difference. The question is, we have a very nice and precise chopper. Why should we introduce a new chopper type, which is in this case the stealth chopper? So we have the spread cycle, which brings the benefit of a very nice torque control, so very, very accurate, everything, so nothing to complain about it. The field reaches a target position, so we are very on the point with our electromagnetic field we are making, and the chopper is auto-adjusting, so you do not need to make so many settings. You will learn later which settings there are, but basically the speed is compensated, and there are some chopper cycles adjusted, and we have a very nice current measurement. So, but there is also a disadvantage. So we see there is a non-synchronized chopper modes. Let me get the laser pointer here. Distortions can be audible, and we always have a few micrometer movement or a little bit noise in that. That is something you hear when you have a stepper motor in standstill or low turns. It turns out that there is a small jitter on the faces. So basically, the reason is that we are measuring the voltage. So what you see here, the green trace, there we have a shunt resistor in the line with a motor coil, and this shunt resistor is measuring or is converting the current into a voltage. So we see here a few hundred microvolt, and then we switch on the coil. The current increases then, and due to the noise, we have a very precise measurement. The chopper terminates the cycles more sometimes earlier, sometimes later, which leads to a jitter of a few microseconds. This can come to ground drops, digital switching, and if you have the other motor coil also used, then this will have effect on the measurement. So there's a small noise which leads to a jitter. So this basically translates that we have here an oscilloscope shot, which you see here, which is a phosphoric oscilloscope. So you see there many chopper cycles laid over. So this is several cycles, and you see here the yellow trace is one end of the coil, the blue trace is the other end of the coil. So you see here the 24 volt are switched off with a certain jitter, and also the blue trace, the other coil, is switched with a certain jitter, which leads to the noise. You see on the upper area there is the green trace, which is the current, and if we push this together we have this sine wave which has a little bit noise on it. Taking a look at the lower side, we see there that we have also the size of the coil, and we have now for stealth chop used eccentric PWM. So this means we have both switched. One goes up before the other, and the other goes down before the first one. So the motor sees first a higher frequency, then we chopper, and you see here also overlaid. We have a PI controller, not a strict current controller. So these are very, very, very close together. So you do not see a jitter here, which leads to a very nice clean sine wave. And this also gives some respects to the supply voltage we should use. But I guess this is something we will explain later in the hands-on training. And what would be our analogies without our bicycles? So here we see spread cycle, very accurate chopper. You have thin racing tires. You can go fast, go precise. Or you have here a gravel bike, which is good for more suspension, and so due to that, has a different behavior. The beauty of these two choppers is they are both coming in our chips, and they are implemented at the same time, and we have a switch over. So we can have automatically switch over because the stealth chop is a voltage controlled mode, which is a little bit more smooth and not that fast in the reaction. So it is used for 0 to lower speeds. And then at the higher speeds, we would use the spread cycle chopper for accurate and high dynamics. And there is a setting you can make in the chip. You can just say, hey, at this velocity, please move over to the one or the other chopper, and then the chip automatically switches in between these both. So you have both of two worlds in your application. So low velocities, low noise, and if you go to high velocities, normally chopper noises doesn't make the difference, because you normally have then also mechanical noises and other effects in the system. So we have our very nice features, which are cool step and stall guard. I hope you had the chance already to go over there and look at the demos. When not, please do so in the breaks. There they are explained also, but basically our normal behavior is that a stepper motor is driven with 100% current. So you normally do not know the load conditions, so you just drive a current that you would have a safety margin for your load. And if then there is an obstacle in the way that increases the load above your planned maximum, then you will lose the position information and the motor stalls. Please keep in mind, the stepper motor is a synchronous machine, and a synchronous machine will, when it's overloaded, lose steps and lose the position. And we can detect a stall situation, or let's say close to a stall situation. So we are measuring the back EMF of the motor, and depending on that shape of the back EMF, we can have a feedback and make a blocking detection of the motor, we can use it for referencing or for a system check while testing or running the motor up in the application. So we have an information about the load angle. We can also use that for another thing. So we have seen motor is 100% current input, and if you have here a load which is way lower, but the high current is in the machine, then you will produce heat, and you do not want that normally. So we have the cool step feature, which is a load-dependent current control. So we have the information about the load angle, and if we do not need the load, we will just, the current, we will lower the current, and the current follows the load. So this is basically what these features are doing. So basically, we have now finished our features which come with our drivers. So this orange part there, like Lars explained, we can take care about everything between microcontroller and the motor leads. So there are also for the microcontroller some options, but this is a different topic. We will not take care. Drivers with step direction interface are normally used for robots or 3D printers where you already have a controller who's doing the spline interpolation, so that an additional motion controller is in this case not needed, but we have several features which bringing our products in a very nice position to make it more reliable, more noiseless, and also more efficient. Here is a small selection, so you see from 2 volt to 60 volts in different current stages, but this list is here more for the aftermath. If you want to select a part, then please take a look in your handout and then make a selection or reach out to us. So the next part is the motion control. We are always getting asked, why motion control? Why is it necessary? And I guess 12 or 15 years ago, there was then the idea, we are from Germany, so we explain everything with beer. So we invented the famous beer slider. You will see also at the demo booth, I guess it's a tea slider or something like that. But we explain bad motion control just with a beer that is getting spilled when we have a bad motion control. We can do it better with S-shaped ramps. And to not get beer spilled, you see this is done when you accelerate in a linear way. But if we use liquid loads, beer sliders are not a typical application. There are not so many in the market. So this applies to all sensitive goods, heavy loads, and so on. You can use S-shaped ramps for the motion control, which lead to a very smooth and predictable jerk in your application. This adds a new block now in orange to our block diagram. So the drivers we have all these nice features, and now the motion controller comes into the play. These are coming with our so-called C drivers. This is exactly the part you will have your hands on later today. So this part comes with a so-called 8-point ramp. What does 8-point mean? So we have seen linear motion is not always the best. S-shaped is very good, but needs some space, calculation power, and so sometimes it's not mandatory. So it comes, depends on the applications. So the 8-point ramp has different values where you can just say at a certain velocity, I just want to have another acceleration value or deceleration value. These can be set independently, and you can adjust your profile according to your needs. In the end, there is hardware. There's not a program processor, there's a hardware block, taking then your settings, and then you just go and say to the motor, move 5 rotations in this direction or move in another direction, and then the motion controller will take care. So it is in real time. So you just send an SPI command. Once this is valid, the new values are valid. So you can also go in a different direction, and the motion controller will consider all these constraints you have set before and drive to the position you want on the point. So we can limit the jerk with a 8-point ramp because you can just adjust it like you want, and then we have the positioning on the point, so no overshooting, no mismatching, it's just hitting the target. Of course, the driver we are looking into it has our energy efficiency with a cool step feature. We can sensorless reference with our stall guard, and of course we have a stealth job on because we have the internal sense resistors. We also have the lossless current measurement. And I guess this comes all in a 5x5 millimeter package. So there we see now some chips which have which are the C drivers, where we have the motion control, pre-driver, and H bridges together. And these are used, if you see, maybe then like Lars mentioned, I guess also CCTV cameras, where you have your application with your image processing, and you just maybe want to go to a certain position. So you go to the C driver and just program it to go there, and you forget about the motion control and take care about your application. And of course here, we're engineers, we run on coffee. We have also for coffee machines, there are adjustments of the grinders, or there's a latte art nozzle which makes some fancy stuff. This is also done with our motion controllers. And like the other parts, we go from very low voltages, battery powered, to in the 48 volt range area. So you have seen now many numbers, many parts. I guess there are some naming conventions. So if you come across one of our parts, you will notice they start after the TMC. This legacy name is, or starting of the chips is still valid. And there are 4 numbers normally. The later 3 numbers are not that important. They have also a meaning. But in the end, if you come across something with 0, we have H bridges. We have heard a lot about drivers starting with a 2. Then we have a pre-driver driver stage, which is going to be controlled via step direction, and so on and so forth. So we have the 5240 later on in this hands-on session, and who can tell me which part it is? Exactly. Here you're having a C driver, so you have the motion controller and everything inside. Some more names are coming with a 4, which are then the motion controllers. We also have for 3-phase BLDC motors and interfaces. Something, if you're looking for an EtherCAT interface, we also have something. And with the 9, we will have in the future maybe parts which include a microcontroller, and these will be then named with a 9. So we have there a clear naming convention, and if you are looking or getting in contact with one of our parts, you will see then these. So we have talked a lot about stepper motors right now. So of course there are also BLDC or PMSM motors, so permanent magnet synchronous machines. In the end, a stepper is also a PMSM, but we use it normally in the BLDC, EC, or electronic commutated motor area. This is a PMSM BLDC motors. And there is a scheme which is called then the field-oriented control, which we also have some products for. So the most dedicated products are for steppers, but also for field-oriented control, we have some solutions. The question is, why should you use field-oriented control? So basically, field-oriented control is the most energy efficient method to turn a motor. Why is it? Because we have a rotor, and then we have, for positioning and commutating, we have then an encoder, and the field, or the electromagnetic field which is surrounding this, this rotor, is always positioned in an optimal way, that we have the most force at the lowest power on the rotor. This gives us highest dynamics and highest speed. So we have done the approach with hardware. So there are some implementations in firmware software, but we have chosen the way to do that FOC in hardware. So you do not need to program a fog, you can parameterize a fog. So this is just by register settings. So this makes it easier to implement it. You can use your CPU you are using. So you might have your task, and in this task now there is a motor application, or something must be moved. Either you take a stepper motor with a motion controller, or you can connect via SPI, one of our FOC controllers. So you can use your controller you're used to, you want to, or in some days, the controllers which are available on the market. So this makes it easy. So you can use your CPU, your tool chain, and so you can drive a very high PWM frequency with a very compared low power microcontroller. So this is the beauty of the solutions, to do that in hardware. So we can go very high frequencies for and low inductance motors. Generally, if we look at the servo system, we have there also, like all other motor drive systems, we have a controller for that, a motion controller. We have a pre-driver and a driver stage, and then followed by the MOSFETs, which are bringing the power into the motor leads. So in the end, we need for this a feedback system. So there are also some SFOG solutions coming up, so sensorless fog. But if it comes down for robotics precise positioning in standstill, this is not very accurate. So we have solutions for encoder, which is fed back into the controller. This is just a selection and a smaller, or let's say a smaller focus or a bigger zoom into this application block diagram. So we have an encoder and the current sensing, and we know from the current sensing we know how the electromagnetic field is. We know from the encoder how the position of the rotor in between the electromagnetic field is, and in the end, then we can match it 100% together. We have then the normal cascade of controllers, where we have then a flux, torque, and position control after another to determine the new current values which are going via the PWM engine to the gate drivers. So this is a nice feature, but not that fancy part. So we have an RTME interface, which is has just basically a different SPI channel on the chip, which can monitor for values of current or position or whatever you want in current control frequency. So we have then 100 kilohertz current control, and you can just pull out the data very fast to get live information about your system. This is a very nice tool. You see there in the back the pendulum demo, which utilizes that, and this is a very nice nice feature, which is not available with other solutions as far as I know. And here you see the 6100, which is because there is a 6, we learned in the naming convention that there we have a 3-phase BLDC gate driver, which then is making the power stage driving the motor. So this is just a small setup where you can which you can take, put behind your microcontroller, and you have a ready-to-go FOC solution, let's say off the shelf or one-stop shop. So we do that in hardware because you can easily get to 20, 25 kilohertz with a processor solution. That's not a big deal. You can also get the PWM frequency higher with a microcontroller solution, but the current control frequency stays then at a low frequency. And we have always our current control frequency in our PWM frequency, which makes a measurement every chopper cycle and then adjusts the current. So this is a very nice feature we have. And so the 20 kilohertz is for some people still the state of the art. Depends if on the motor type, but we have seen that for many, many motors, 100 kilohertz is a good upper limit. So maybe you just need 70 kilohertz or 60, depends, to reduce the current ripple. You can just freely program it. So it's not set to 100, so you can program it and have all the features of faster settling times. The torque is following faster, and the system gets more dynamic, and the position stability will be also very, very good. And if you take a look at these scope shots, what you can see there is that the current ripple you are experiencing will be way less on the motor leads. And if it's on the motor leads, a lower current ripple, you will also see on the supply. You can make smaller capacitors in your supply. You can maybe make some smaller EMC filters also. And this is a nice thing of this hardware solution for the FOC. So I guess we have another nice topic, which again Lars will lead you through.
Okay, so now we talk about smart solenoid drivers. So we can turn a lot of things we learned, but how to actuate essentially like solenoids, proportional valves. So what you see here, let's concentrate on the graph on the left here. The y-axis is the current, and the x-axis is the time essentially. And if we switch like a coil that you see here on the right, like a solenoid, which is essentially a plunger that when activated moves out, for example, and when deactivated by a spring is set back to the 0 position, we can see essentially that's how the current profile would look like with a typical approach. And typically if you drive like solenoids this way, you wouldn't get noticed of it, right? So what our Max 22216 does, our latest solenoid driver generation, it essentially gives you the feedback about the travel time, the reaction time, and also this so-called back EMF dip. The back EMF dip indicates when the plunger actually moved to the position. So it gives you a lot of additional feedback without additional sensors, right? So we have 4 half bridges with closed loop current control, also voltage controlled mode. This enables highest energy saving because since we can detect when the plunger moved by this back EMF dip, we can actually reduce the current more early to let it be more energy efficient, but also drive as cool as possible. And we get all this feedback from the solenoid, right? Which also enables predictive maintenance in your system, essentially. Yes, and here we see this IC, like a very tiny 5 by 5 square millimeter package. This is our evaluation board, right? And this is like the space with passive components that's needed to essentially have 4 half bridges activated, where you can see on the right, you would, for example, connect your solenoid. And we have like very smart features implemented, like the detection of plunger movement, DPM, and this is like the space that you would need on a PCB if you build it up discrete. Another feature that we have integrated is fast demagnetization. So with valves you might actually need a fast demagnetization mode, and this is the space on a PCB, how it could look like, so quite some space needed to have this in the circuitry. And also the closed loop current control mode that is integrated. As an example, it's quite quite a big design, and we have all those features implemented in this tiny little IC essentially. And now we have a quick look on our Brush DC portfolio. So if the Brush DC motor is the selection essentially based on the requirements, then we also offer quite some parts to drive those Brush DC motors. So you can see on the right side an overview of our features that we offer. So this essentially gives you an overview, right? We don't focus too much today on Brush DC motors, but you can see that we have those legacy Maxim Brush DC parts essentially available for different voltage and current ranges and those kind of features. So depending on what you need, we have parts in our portfolio. Okay, we talked a lot about integrated circuits. We explained that we also offer like solutions. So let's start with our so-called cookies. Essentially system on a module, where you can see here like two variants. The TMCM-1690 is our three-phase FOC gate driver cookie with current sense amplifier and two like interface options, and a stepper TMCM-1290 is essentially one solution to activate stepper motors on your electronic. So it's a very neat concept where depending on if you, for example, have two brushless DC motors in your system and three steppers, you could simply choose two of those, three of those, put them on your electronic, and essentially have those kind of motors activated in your system. As there is no implementation of software stacks needed, this is all integrated in this firmware, no royalties needed, space saving through integration, and can essentially be soldered on your own electronic. And here we have it a little bit more detailed. Here we see the example of the TMCM-1690, the brushless DC version. State-of-the-art motion control up to 48 volts. The benefits is essentially that you have flexible interface options with the integrated protocol stack. So essentially you communicate to this motion cookie via one of these interfaces, and then there is a firmware running where you can send simple commands to essentially drive your motor without extensive coding essentially. We have all the diagnostic and protection features as we use our integrated circuits on those solutions, right? And now you might ask, okay, it's nice, motion cookie, but how should I evaluate this? So if we skip to go to the next slide, transition here, we offer those evaluation boards where the motion cookie is pre-populated with all the different interfaces that are available, a supply block, the power stage. So as this is the brushless DC version, we need external MOSFETs. As you might know, with brushless DC motors, it could be that you run from 100 milliamps up to 100 amps. So having like one power stage that covers them all is actually something that would be difficult. So we let the customer essentially design it based on their needs. We have a so-called TMCL programming language where you can download scripts. So this little module can actually run on its own, if you will. And it comes in tape at reel. It's ready for pick-and-place machines to be essentially soldered on the electronic. And now one step further, as we saw, the motion cookies are without connectors for your own electronic. We also have our board level and pen drive turnkey solutions. And here we start with the board level solutions like modules. You can see some examples here. This is our TMCM-1260 that is very powerful for stepper motors using our latest technologies. Here we have an example of a brushless DC solution. So that's a very tiny, very powerful brushless DC FOC controller and driver, the TMCM-1617 in different interface types like even EtherCAT, RS485 and CAN. Here we have a multi-axis stepper board, our TMCM-3351, where you can connect up to 3 motors and also encoder feedback for closed loop stepper control. And this is actually the block diagram as an example for this board. And essentially, these are a good option if you have a short time to market. So you have maybe a device that needs to be done in a year or something, and you don't want to do your own motion control on your own. This module activates essentially the motion control for you. that needs no development resource or almost none, right? It has standalone capabilities, so you can download the program on it, so they can run on their own, and various interface options, RS-45 CAN, USB, EtherCAT, you name it, and up to 6 motors per single electronic, but you can obviously use multiple modules to activate even more. And yeah, this is available as open loop and closed loop options. Yeah, here it's maybe some more details. We offer digital IOs, analog inputs. As mentioned, we can use the standalone mode, but you can also send, obviously, through the interface, direct commands. We have the CAN Open and TMCL firmware, depending on what your requirements are. And here we see on the right, which you also will later use, our TMCL IDE. This is how this 3-axis stepper module, for example, would show up in the IDE, where you have great tools with graphs. This is like this programming tool here, but you can see there is a lot of things that you can parameterize, evaluate, and tune. One step further, we also offer like pen drives. The motor essentially directly electronic connected to it, so even easier to operate. You connect power, you connect an interface, and you're ready to go to drive a motor. Very easy to set up. A one-stop solution. And what's neat, if you look at this motor here, we have a little magnet here on the back to essentially enable an encoder feature. So we have a sensor on the back of the electronic, and here you can track the position essentially. We also have options with enclosure, and yeah, these are great options if you need a solution that's ready. And here we show some success stories, essentially some applications that our solutions are integrated, starting on the top left, a pipetting robot, like in the lab automation area, a 3D laser scanner, which essentially scans, for example, a car, like the profile, but obviously you can scan a lot of things also when looking in additive manufacturing, scanning objects for preparing a print. This is like a project where we actually activate very accurate, precise motion for one company. So they are taking care about the algorithms, how to react on different sensors and ground when moving, right, with this prosthetic. But we essentially provide the electronic to drive this powered knee and ankle essentially. Then the coffee machines, to grind, move and lift the nozzle, but also, as Dirk already mentioned, they do also some very interesting like latte art, where they move the nozzle to make interesting figures into the milk foam essentially. Then we have in this eye inspection device like solutions, and in general in lab automation. So this is of course not everything. So everywhere there's motion needed, energy efficient, smooth, as silent as possible. We have essentially solutions that would be a good fit. Okay, and then last but not least, we look into our tools and resources. As mentioned, we have our TMCL IDE graphical user interface that you see here on the right, that you will, after the lunch, have a hands-on with. We also have Python packages available. So if you do your own design, you might want to start exploring with Python. So we available a library for that. An API that's also available on GitHub. An Eclipse project, which is essentially the firmware that's running on our evaluation boards on the microcontroller. So this is also open source if you do your own designs. And then YouTube videos going over the features and introducing products. And if you want to start exploring when you want to do your own electronic, we offer this evaluation board concept. These are like all these white boards are essentially part of our evaluation boards, where you see on the left this communication board. In the middle, in this case, it's an EtherCAT interface chip, and this is a brushless DC power stage, essentially. So also you already have or will get this evaluation boards with our TMC 5240 stepper driver. And it's a flexible solution. As you can see, you have this connector and you can essentially exchange whatever IC you want to explore with the solution. Easy to use with our TMCL IDE. Fast tuning tools. It's open source, as mentioned, for the layout files, schematics, firmware, essentially. And it should provide you a good out-of-the-box experience, right? Connect to USB, download the IDE, connect a power, and then the motor. You should be good to essentially operate your motor.